moving on to example 2, I wanted to refresh your memory on a little something called a co-terminal angle. Co meaning same, terminal meaning ending. Because what they're going to ask us to do now is find 3 pairs that are different, or that's what they mean by other pairs of polar, again, the new form that we're dealing with, for this point right here. And hopefully you can see what we're dealing with there. And if not, what can we always do in order to see what that looks like? That's right, just draw a quick sketch. Now again, you don't need that polar form, but you need to know that you're going, hopefully, to do the angle first and then the radius second. Now, in a lot of your problems, they'll probably tell you that they want to keep all of your angles between negative 360 and positive 360, or negative 2 pi to positive 2 pi, because otherwise you could always do what to find a coterminal angle? And hopefully you said add or subtract 360. How many times? As many times as you want. So yeah, you could always get another one of these polar coordinates by just not thinking really and adding, or subtracting 2 pi or 360. But in this case, they want you to do a little bit more inquiry and thinking. So if I was to go negative 110 degrees, I know that that is going to tell me to go negative 90 plus 20 more. Or remember, we always did our reference angles to the x-axis. So that wouldn't quite be 180. I'd have to come back 70 degrees. So when I do that, I know that I'm facing this direction, because that would take me my negative 110. And I am going to march out a radius of, since I'm facing the direction of that, positive 5. So in order to do this, I will go ahead and put that. And how do I know that's a length of 5? I don't. I don't have my polar grid and I don't need it. But I do know that I can just put 1, 2, 3, 4, 5 tick marks, just like we always did when we created this. All right. And that would take me to my point they're calling P. All right. Now I'm going to do a little bit of labeling as well. I'm going to put my reference angle right here of 70 degrees. And we already know our radius is equal to 5, because I need to find 3, they mentioned, other points that are actually that exact same point, just different ways to get there. So one thing that I can do to find my 3 different options to get to that same point P is obviously what is not going to change. And hopefully you said the length to get there. It's always and still will be 5. But remember, some of them might be negative. So of those 3 options, we need to then fill in whether they are going to be positive 5 or negative 5, and what the angle of rotation would be for our theta. So right now we had obviously gone negative 110 degrees. How could we get to that exact same spot? Well, remember we said we could take negative 110 and add 360 degrees. So by doing that, if I add 360, I know I would be at 250 degrees of rotation. And if I did that though, careful, I know I'm going to be rotating from my positive x-axis. So going this way, I would then want to rotate that 180 plus 70 more, as we wrote with our reference angle. So we got 180 plus 70 more to get to my 250. And then you can see what direction I'm already facing. Always in the positive, we start, and I'm going to go up this time because it's positive 250 degrees when we added 360. And that's the direction I would be facing, which is the exact direction I would want to go. So all I'm going to do is go out 1, 2, 3, 4, and 5 tick marks to plot my point. So that means I wanted to go a positive 5 direction after rotating 250 degrees. So that is definitely another option for us to go to get to the exact same point P. But now, obviously, since I've used this positive 5 now twice, I'm thinking I'm going to have to use negative 5 twice as well. Now I've also already used 110 in the negative direction and now 250 in the positive direction for my angle theta of rotation. So I'm also going to now try to figure out what would I have to do to go -5 this time. And so this -5 is going to be requiring me to be in the opposite direction. So since I already have this angle theta here as a reference angle to my x-axis, I'm going to then start in the x-axis and rotate this now positive 70 degrees. And if I do that, that would also be my reference angle. Now notice what direction I'm facing to get to this point. I'd be facing that direction, the opposite direction from where I want to go. So if I rotate 70 degrees, if I go the opposite of that 5 units, then that would then take me 1, 2, 3, 4, 5, again, to that point P. So there's another version of that same point P by rotating 70 degrees in the positive. And then since I'd be facing this direction, I would go negative or backwards 1, 2, 3, 4, 5 when I rotated that 70 degrees. So again, just like we did before, when we added 360 to that, I will do the same thing, but this time I will subtract 360 because we would like to stay within those parameters. So I'm going to take that 70 degrees and I'm going to subtract 360 to it. And we know that almost works out perfectly. If it was 370 minus 70, that would be 300. So we owe an extra 10. So negative 290 degrees. Meaning I would start in the positive x direction and I'd rotate 180 degrees. Another 90 would be at 270. And then I'd have to rotate 20 more, because I know that's a reference angle 70 there. I'd have to rotate 20 more to get my negative 290. However, if I rotated that negative 290, starting here and negative meaning down, all the way around 270 plus 20 more, to get that 290 degrees, again, I'd be facing the opposite direction I would want to go. So I'm going to have to go -5. 1, 2, 3, 4, 5 to get back to that original point P. So you can see there are several different options to get to the same place just between negative and positive 360 degrees, one full rotation around. Okay? So I want you guys to give me some, but this time I'm going to make it a little bit easier and a little bit harder at the same time. I'm going to say I only want 2 pairs of polar coordinates. But this time, instead of giving it to you in polar form, I'm going to start it with being in rectangular, meaning I gave you an X and a Y value, and you need to give it to me in polar form, which means I need an R and a theta. So first thing, we have to change our current form, which is X and Y, and find what the original polar form would be so that we can then supply them with the 2 polar coordinate form of that point. So I'm going to start by giving myself a visual and drawing it. And now that I have that, I can then draw from my origin to that point so that I can create my right triangle and hopefully find this reference angle theta. And as we reviewed in the previous section video, hopefully you can see that the X, the Y, my 2 side lengths of this right triangle resemble one of our special right triangles. Is it the 45, 45, 90? Right away, you know that it shouldn't be because these are not the same. And therefore, we're looking for the 30, 60, 90. And hopefully you can see that, yes, indeed, this would be the A value. This would be the A root 3. and therefore this would have to be 2a, which gives me a length of 12 for my r. So I already have the r being that of 12. I'd also then have to figure out what the theta is. And remember, we can either go positive 360 or negative, whatever. In this case, since we're in quadrant 4, I would just go back or negative whatever that angle is. And is it either the 30 or the 60? Well, remember 30 degrees is smaller than 60. And since the side length opposite that angle is bigger by root 3 than this one, then I know that my reference angle has to be 60 degrees. And so I'm going to write this in as 12 comma negative 60 degrees. Now remember, I haven't given them two other pairs of polar coordinates. This is just one. And all they asked for were two pairs of polar coordinates. So I've already given them one for that. How can I quickly give them another? Well, I could just easily and quickly add 360 degrees to that and still march out that 12. Because if I add 360, that means I'm just going to go around my circle and get right back by going 300 degrees. And that'll be fine. If you paused it and actually tried it yourself, then you can find other answers. All you'd have to do, since we got the two positive cases so far, positive R values with one positive and one negative angle, we could have also found two negative radii, values of 12, which remember what negative means? The word opposite. So I would have to be facing in the opposite direction. And remember, we already found the reference angle of 60 degrees. So the quickest, easiest way to get facing that opposite direction, which we already have here by putting the negatives, would be by rotating this around 180, but less 60, so 120 degrees in the positive direction. Or I could go from here down negative 180 plus 60 more, which would be negative 240 degrees. So these four options would be possible answers when they only asked for two. I probably would have given them the first two that I gave you with the obvious first choice and then just adding 360 to get the second. So remember, you can't just continually add 360 or subtract 360, even though it would get you back to this original point. They're usually going to ask you to be within 360 degrees, either positive or negative. So make sure you read the directions in these. But pretty simple. Whether they give us the polar form initially or, in this case, the rectangular. We just got to do a quick conversion. So this third example, we're going to change gears a bit, and they're going to ask us for this original rectangular equation, something that we should already know the graph of, and they want us to do two things. They want us to give the equivalent polar equation of this and then sketch its graph. Now, if they ask me to sketch the graph of this, I already know how to do that. So the very first thing I would do is that I would go ahead and graph this rectangular form of this equation, which you should know is a line in our mx plus b, or slope intercept form. So remember, we do the order of the alphabet. We're going to start with the b, which is our y-intercept. And I'm going to start by going down 4. And then I'm going to use the m, the slope, which is my rise over my run. Remember, we rise to our y's and run from our x's. And I have now sketched the graph. However, that was just the last part. They also asked us to find the equivalent polar to this original rectangular equation. And remember, rectangular is when we have x's and y's involved. Polar is when we have r's and thetas. So what we're going to have to do is take this original y equals 2x minus 4, and we're going to have to revamp the look of it to get rid of the x and the y and only have r's and thetas involved. But hopefully you remember, we talked about this earlier and reviewed it, that we knew that x is equal to r cosine theta and y is equal to r sine theta. So all I got to do to get rid of the x and the y is use what we like to call an identity, what it's equal to for each of these. So I'm going to replace all of that original y value and the x value with what I know it's equivalent to. So the y value, remember, was r sine theta, and our x value was r cosine theta. Now, obviously, I want to try to make this look a little bit nicer. So just like all of our rectangular equations had it to where it was y equals, we want to do something similar. And which of those two do you think would be easier to plug in and then work out to solve for the other? Well, remember in rectangular, we actually said it was easier to just plug in some x values and then do the 2 times that, subtract by 4, and find our y value. So hopefully you gave it some thought and came up with it would be easier to plug in angles rather than trying to figure out what the angle is given some radius. So we need to then take and solve each of these for our r. So we're going to start by doing that by first rewriting without parentheses. In other words, multiplying the 2 times the r cos theta, which is also all multiplied together, and we get 2r cosine theta minus 4. So in order to get the r's by themselves, I need to first start by getting the r's on the same side. So I'm going to go ahead and subtract the 2r cosine theta to both sides. Now remember, we only know how to add and subtract like things, and those are definitely not alike. So on the left side, I will still have r sine theta minus 2r cosine theta. That all cancels out to just be equal to a negative 4. So how do I take now 2 r's and make them into 1? Hopefully you remember a little thing called factoring from your algebra careers. Each of these have an r, so since they are multiplying, we're going to divide or factor out that r. That will then cancel out to give me sine theta minus 2 cosine theta equals a negative 4. And lastly, to get that r by itself, I could then take, since it's being multiplied, and divide both sides by this sine theta minus 2 cosine theta. That would then give me what r is equal to. In terms of theta. Now, if you don't see this as a possible choice, if it's multiple choice, then what do you have to make sure that you know you can do to this to make it look just a little bit different? Everything might look identical to what you have, but some of the things might be the, what'd you say? Opposite? That's right. And remember, what we can always multiply by is a funny looking 1. So if I wanted to multiply and make all of the positive on top and the opposites on bottom, I could just multiply by -1 over -1. And that would give me an alternative version of this of positive 4. And then I'm going to write the positive thing first. So now 2 cosine theta minus sine theta. So either one of those, if you have, make sure that you know that they are actually equivalent. They just will probably have this as the solution compared to a negative on top. All right. So make sure if you do not see your answer that you may have to multiply by a -1 and you know how to do that so that everything becomes the opposite on top and bottom. So you're still just multiplying by a fancy 1. Okay. Now don't forget, they actually asked us to sketch. Now, if you did all of that work and you came up with either this or that, and they asked you to graph, you would have had no idea that it is actually this line right here. And if you didn't, you would have had to have plugged in a lot of nasty angles like 30, 45, 60, and all the quadrantal angles, 90, 180, 270, in all 4 quadrants to get all the way around, evaluate that just to find at each one of those rotations, the 30, the 45, the 60, the 90, that you would have had to have done, how far you would have had to have marched out and plotted that point and plotted that point and plotted that point for each and every one of these, just to find that it was this line that you should have known from the beginning. So if you remember the graph in the rectangular form, then just graph it. Don't change it to this crazy looking form or that. And then try to graph something that you have no idea what it looks like or how to even do it yet. My opinion is do it the easiest way possible. Okay. They did not specify other than that we had to sketch the graph. Well, guess what? Here's the graph. And I got it from the rectangular form rather than the polar form. So might as well do it the simplest way. All right. So just to give you one more look at it, I wanted to give you a different type along the same lines. So if you want to pause this and try it on your own, go for it. But this one, very, very simple. Because you should already recognize, just like before, that you're trying to change the x and the y into r's and thetas. And remember, every once in a while we had equations in algebra that only had just an x or just a y. They were special circumstances. If you remember, we already know that x squared plus y squared is equal to r squared. So I can simply just take this and replace it with r squared. Just don't forget that we wanted it to be r is equal to something. So I would just simply have to take the square root of both sides, which means I'd have to put the plus or minus, and take the square root of each to get this. Now, again, most of the time they're not going to put the plus or minus. They're just going to say r is 5. Because remember, there's no such thing as a negative radius per se. Even though when we've been graphing points, we've been talking about opposites or negative lengths. Okay. So when dealing with this, hopefully you recognize at the very beginning that the graph of this was what is called a circle, centered at 0, 0, and a radius of, 5. So even though you hopefully remember that and studied it in algebra, and you knew that the center was 0, 0, there was no shift, no HK associated with it, but there is that square root of the 25, the radius of 5, you know then how to graph it. And you don't need polar paper, graph paper to do this. Just go from your center 0, 0 out 1, 2, 3, 4, 5 in both the X, positive, negative, and the Y, positive and negative. Because once you have that, then that means you have enough to graph. You can then graph your circle with the radius of 5. Now, again, my tick marks are off, which is why it didn't work so well, right? But if you have graph paper, much, much easier to graph. Okay, so that's it for that one. Very simple when it's in rectangular form. If you recognize it, then graph it as is, whether it's the equation of a circle, like we had in part B, or an equation of a line. But in order to change it from one to the other, remember to use these things up here that we talked about to go from one to the next. Or sometimes you may have to square it if they're not already, so that you can replace an x squared plus y squared with what we know is equal to r squared. Okay, so what if they give it to you in polar form? Now you don't have the luxury of graphing it in rectangular form because you don't have it in that yet. But one thing we could do, just like we have been a lot recently, is going from one form to the next. So even though they gave it to me originally in what is called polar form because of the r and the theta, then I want to find the rectangular form equivalent. And then once I have that, hopefully I'll recognize what it is and graph it because I don't know what that looks like currently. So r equals 2 cosine theta. I will then have to graph, which I'm going to try to change it first to that rectangular form from polar form so that I can graph it last. So how do we change this? Well, one option would be to just take what I know. And the one thing I do know is that cosine theta is always equal to x over r. Because even though I don't have an r squared like I did in the previous, I can go ahead and multiply over by r to both sides to get r squared is equal to 2x. Because now that I have that, I can then get rid of the last piece, which is the r squared, by replacing it, just going the exact reverse of what I did earlier with an x squared plus y squared. So now my task is to figure out what kind of graph this is and put it in its standard form, what it standardly looks like, so that I could then graph. Because right now, I don't know if you guys recognize what this would be. It looks a lot like the previous one we just did. It has an x squared plus a y squared, but it also has this 2x on the other side, which means yes, it is a circle, but instead of the center being at 0, 0, it's going to be shifted. And it looks like only in the x direction. So I know it might have been a while since you've done this, but that's why I wanted to go over it with you all. That would now give me x squared minus 2x, and then plus y squared equals all on the other side of 0. Now, I left a big gap for a reason, because if you remember what we have to do in order to get this in its standard form of a circle, we're going to have to add and subtract a number on the same side. Now, some people like to add the same number on both sides. Either way is fine. I just like to do it this way when we have leading coefficients in front of the x and y squareds, because we're going to have to end up moving it over anyway. So whatever you choose. How do we find that number that goes in there? It's very simple. You just take the x or the y and you take half of it and then square it to go in that square. So half of -2 is -1, squared is 1. And the reason we're doing that is so that we can actually factor what is given there. Now, the cool thing is I don't ever factor because I forced it to be this way. And I'm going to force it so much that these two factors will always come out the exact same. And if they come out the exact same, then I know I can write it as something squared. Hence the name completing the square. And what's always going to go in there is going to be your x and your x to get your x squared. And whatever half of your middle term is, including its sign, will go in the second slot. So that was the -1 and -1. Because when I multiply and distribute that out, I know a -1 times a -1 is my +1. And when I do the other distributions, I would get my -x and -x, which is -2x. So I always skip that step and just simply write it like this. So that will leave me with an x minus 1 quantity squared Then I will take this -1 and add it over to the other side so that I'm just left with the positive y squared, all equals to 1. And that, my friends, is what is called the standard form of a circle, which now allows me to graph. So now that we have it in the standard form of a circle, we'll just quickly draw our axes with our center of 1, 0. Remember, always taking the opposite of the thing inside of the squared part, and then always taking the square root of the piece left over on the other side. So that would give us a center of 1, 0 and a radius of 1. So now that I have my graph of my circle, I know you're impressed. That's a good circle, isn't it? I'm going to show you real quickly that if I took this equation and plugged it into Desmos, what it would look like if I was to graph it the original way in polar form versus what I had to do a bunch of arm waving for to get it into my rectangular form. So if I took r equals 2 cosine theta, and you can see I have it there with a few others that I'm going to show you later on, and I graphed it, I get my center point right in the middle at 1 and my radius of 1 to get my circle graph. Okay. So it's a good way to check and make sure that you did your answer and conversion correctly for both your graph and your rectangular form. So let's take another example and see if we can work this one out, which is a little bit more difficult to work with because first of all, it has fractions and then it has a trig function in the denominator. So where do you think we should start? And if you want to try this on your own, go ahead and pause it at this point, give it a shot, and then we'll come back. But I'm not going to start with a graph because I don't know what that looks like. So I'm going to change it to rectangular form in hopes that I know what that graph looks like based off of its equation. And we're going to have to make sure we put it into that standard form. So first things first, I don't like the fact that I have a fraction, so I'm going to multiply over by 1 plus sine theta to both sides. Now remember, that means if I put this over that and canceled out, I would have r times 1 plus sine theta, all equals now just 4 on that side. And since it's in what is called polar form, because I have r and theta, I'm now going to rewrite my sign as what I know it's equivalent to. Because my goal is to get it in just x's and y's and get rid of any r's and thetas. So I've started by rewriting this sine theta as y over r, and then I'm going to go ahead and distribute that r to get r plus, now these r's would cancel out, and I would just get y equals 4. So that's a good start. However, I still have an r there. And the way that I can get rid of an r best is when it is squared. So I know it seems kind of redundant, but I wanted to get rid of the fractions just to make it a little bit easier. I'm going to move that back over and put 4 minus y by subtracting the y over, because now I can go ahead and take that r, now that I have 4 minus y, and do what to both sides? Hopefully you said squared. Because when I have r squared, I know what that's equal to. So rather than distributing the right side, I'm going to just first take and rewrite the left side as what I know it's equal to, and that's x squared plus y squared. Now, because I have an x squared and a y squared, and I'm going to have more y squareds, I'm going to actually take the 4 minus y and distribute it out, which doing that, I get And then I will move some things around so that I can try to get this in its standard form. So I'm going to go ahead and add 8y to both sides and subtract a y squared. So that would then give me those to cancel out. On this side, those also cancel out. So the only thing left is an x squared plus an 8y equals 16. Now the previous problems have had just an x and a y squared, and we knew it was a circle. But this time, the y is not squared, which hopefully you remember means it is a, pause for dramatic effect, parabola. So that means we are tasked with having to get y by itself. So I'm going to start by subtracting the x squared over. And now I got 8y equals negative x squared plus a 16 there. And lastly, I can go and take this and divide everything by 8, which would finally get me to have my y equals rectangular form that we're used to. And I'm going to write this as negative 1/8 x squared plus 2. And if you now recognize that this is our standard parabola, y equals x squared, facing downwards, negative meaning down, 1/8 meaning it's going to move 1/8 as fast as it normally did. So it's going to be a little bit wider. We called that a vertical shrink or stretch. And then this plus 2 is going to shift all of my y values because it's not being done to the x squared part. And it's going to be adding 2, meaning we're going to move everything up 2 vertically. So when I go to graph this, because I now have changed it into that form, I know that I can shift it up 2, plot my point, and then I know it's going to be going down much wider than normal. Now, if I wanted to find exactly where it crossed through the x-axis, I could go ahead and find my intercepts by letting my y be 0 in solving. Okay, so we could definitely do that. I'm not too worried about the exact graph of it, and I can even show you on Desmos that it should come out looking something like that. But remember, that was based off of my rectangular form rather than the original, which I'm going to show you if I type that in, what it would look like. And by the way, hopefully you know it should be the same because this is just an alternative version of that original polar form. So 4 divided by 1 plus sine theta would be the second equation down. And if I click on that, hopefully you can see we are just shifted up 2. And then again, we could have found the x and intercept on both the positive and negative side would happen to be 4. Wider than our normal parabola that we have when it's just x squared or negative x squared. Okay. So, of course, they're going to ask us to graph these things. And I'm going to do it without any tech first and just show you how and what you would have to do in order to graph an equation that's in polar form. And then we will never do it again, at least in this class, since it is our last section. All right. Remember, this is solved for r and given in terms of theta. So that means that they're saying, we'll tell you what r is equal to if you plug in theta. Now we're plugging theta into cosine, and then don't forget when we find the value of cosine, we will then have to add 1 to find what our r is. So I have it broken down here into what are called t-charts. I don't know if you guys remember those. Way back when we didn't know how to graph a line, this is actually what we did. Now they don't look too much like a T right now because There's more parts to it. I'm going to start by evaluating cosine theta, then I will add 1 in order to find my r. And what angles do I want to actually plug in? Remember, I told you one of the most important things in all of trig are reference angles. So I'm going to start with those. And not just reference angles, I'm going to use the quadrantal angles as well. I'm going to end up going all the way around this entire circle. But I'm going to start with the quadrantal angles, 0, 90, 180, 270, and then back around to 360. And then I'm also going to do the 30, the 45, and the 60 in quadrant 1. And then I'm going to do the 60, the 45, and the 30 in quadrant 2. And then I'm going to do the 30, the 45, the 60, the 60, the 45, and the 30, so that I get all the way around this thing, because I know once I get there, I will have gone one full circle, period, we used to call it when we graphed. And I know everything will repeat after that. So I'm going to start with 0 degrees. Then I will do the 30, 45, 60. And remember, that will take me to quadrant 1. And once I have that, then I will go to 90. And then I will do the 30, 45, and 60 for that as well. This is what we called the unit circle, remember? And so just to kind of show you how all of these values are going to come out being the same with the exception of their sign, I'm going to write it down like this. The next one would be 120, and then 135, and then 150. And that would then take me to the next quadrantal angle, which would be 180 degrees. And once I have that, I would then have been here, and then I could start on the others, which would be, that would then take me to the next quadrantal angle of 270, and then I'll hit all the reference angles in quadrant 4, which would be, and doesn't this look like fun? This is why we learn how to change things from one form to another, because sometimes it's much easier to do it one way than the other. But in this case, we wanted to actually work this out so we could see what these things look like. Now, one thing I'm going to do is make sure that you recognize that this is quadrant 1. This is quadrant 2, quadrant 3, and quadrant 4, with all the reference angles in between my quadrantal angles of 0, 90, 180, 270, and 360. And since we're dealing with cosine of all of these, we really, I know it looks daunting finding all of these values, but in reality, all we need to do is recognize that these are quadrantal angles for cosine, which remember we know cosine of theta is equal to x over r. And since we're on the unit circle, we can just focus on the x values. So x here will be a length of 1. Here, 0. Here, -1. Here, which is 270 degrees, back to 0, and then back to 360, which is equal to 0 degrees, which would be my 1. So before I actually go and plot these points, I'm going to find all the others. And I already recognize that some of these are going to be the same. This is a 30. Well, where are all the other 30-degree reference angles? Since I know this is a 30-degree reference angle, I know so is this, so is that, and so is that. And each one of those are at 150, 210, and 330. Meaning they're all going to have the same value other than the fact that some are going to be positive and some are going to be negative for cosine. And so I already know, since I'm in quadrant 1, these are all going to be positive values. In quadrant 2, they're going to be negative values. In quadrant 3, negative values. And quadrant 4, be my positive values. Then all I got to do is find the value of 30, which we said the value of 30 for cosine was root 3 over 2, which means this is also going to be root 3 over 2, root 3 over 2, and root 3 over 2. Just be careful to not always put them in the first slot, because remember, we are going along the x-axis for reference. Okay, then I will go to the next, which would be 45 degrees. And the 45 would be right in the middle of every single quadrant. And therefore, we already have the positives and negatives, so we know that we get root 2 over 2 for cosine of 45. We already filled in the positives and negatives. We're all good there. Just don't lose those. And then lastly, the cosine of 60, which again, those reference angles would be a little bit different. Here, 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 and there. We already took care of the positive and negative, so what we're really looking at is what the cosine of 60 is, which is the easiest, 1/2. We just had to make sure that we knew if it was positive or negative. Now, here's where it gets a little bit tricky. Remember, that is not the actual value for r, because that is just what cosine theta is. We actually want to take and add 1 to it. In order to find what r is. So the current form of these things is in fraction form. And if I'm going to graph these things, I just want an approximate. So in order to approximate what root 3 over 2 and root 2 over 2, I already know what 1/2 is. I can say, not approximately, but that is exactly negative or positive 0.5. So all I have to do is approximate the others, again, keeping their signs in mind. And now that I know the square root of 3 over 2 is approximately 0.866, I will then do the same type of thing with root 2 over 2. And now that I have all those values, I could finally wrap all this up by taking those values that we just found for cosine of theta for all those different angles all the way around our entire unit circle and add 1 to them. So when I take the 1 and I add 1, I get an r value of 2. For each one of these, and hopefully you recognize where I actually made a break on all of this and why. Notice all of my R values, they started at 2, went to 1.866, 707, 1.5, 1, 0.5, 293, getting smaller and smaller and smaller all the way to 0. And then at 0, right at that 180 degree mark, it went back to 0.134, 293, 0.5, just like we had here. Then to 1, 1.5, 1.707, 1.86, all the way to 2. It went back the other direction. So when I actually go to graph this, remember how we graph polar is I mentioned that every single one of these points is written as r theta, but I told you to do the angle first and then walk out the positive or negative radius that they tell us. Now, the cool thing is every single one of these is positive. So all we have to worry about doing is rotating that specific angle measurement. So that first pairing I would have here would be actually written as 2, 0 degrees. And so if I went over here and plotted that point, I would start from my origin. I'd walk out a 0 degree radius turn and 2. And there's my first point. Then to get the next one, I would write it as 1.866, 30 degrees. So this time I would rotate 30 degrees And then I would walk out that 30 degrees, 1.9 almost, not quite to 2. So somewhere around here, and plot that point, and so on and so forth. So I'll do that really quickly for you, and then you can kind of follow along. Now, if I stop here and actually start to draw this, I would have started here, gone to that value, that value, that value, and kind of looped around all the way back to 0. And that, remember, was the first half. And hopefully you can see it kind of starts looking like a shell or a spiral shape. But then remember what happened at that 0 after we went 180 degrees. We went 0, 180. We then noticed that all of these values started going the other direction that we had originally. Starts regrowing that shape that we had originally. So graphing that real quick for you and connecting those points for everything in between that we didn't do, all those other angles. We only did the reference angles. You can see we get the other half of that. That looks symmetrical, like we saw with all of our X and Y values, our R's and thetas. So pretty cool. Very labor intensive. I tried to go slowly so that you can kind of understand where all those came from. Wasn't too bad because we know our reference angles, and the only thing that's going to change are the positive or negativeness of them, but still quite arduous. So I'm going to now show you how to graph this same thing using technology. And you're welcome, because this is how I'm going to have you do these from here on out. So have fun with this. I suggest you use Desmos. You can use whatever program you would like, a graphing calculator, whatever. But let's go back up and graph our original 1 plus cosine theta using Desmos. So you can see the third bullet down there is my 1 plus cosine theta. And I'm going to just go up here to the wrench and change it from radian measurement to degrees. So see that there? Changes it to degrees. And now you can see that if I was to plug this in, boom, it's done by a click of a button, or you just have to type it out. Still get that nice little shape there. That they have names for them all. You guys can explore it, check them out. But again, we're going to be dealing with these things called roses and the spiral of Archimedes. So check them out. They're fun to play with and see how these things behave.